All right, what I'd like to do with today's video lesson is to do a quick breakdown of graphical versus analytical solving of quadratic or rational inequalities. A lot of vocab there. So what we're talking about basically is we're going to solve inequalities instead of equations, and they'll be either quadratic in nature or they'll be rational in nature. And in either case, there's a way to solve this using a graphical approach with algebra, or there's a way to use a strictly algebraic approach. So I'd like to discuss both. I'm a proponent of graphical theory because that's the way I see the world visually. So what I see is a parabola on the right-hand side that is opening up and shifts the vertex from the origin up 6. So that's the gist. It's not a very decent graph. It's not a great graph, but it tells me in general how the behavior of the right-hand side of this inequality will be. And on the left-hand side, I can get the x-intercepts of 0 and 5/3 and the fact that it's opening up. I also know that this is opening up at a slower rate than the blue graph is because this is a 3x squared versus a 4x squared. So the vertical stretch factor is slightly different. If there are going to be intersections, especially if this comes from a textbook, chances are there will be some intersections. According to my graph, if there are going to be intersections, those are going to happen right here in the negative realm. It's only going to be a small area, if at all, where the blue graph dips below the red graph, or rather where the red graph is above the blue. Notice here, I'm looking at the red graph as the left-hand side, should have values for y being above the y values of 4x squared plus 6. So that only happens in this small little interval right in here. And again, looking at the a values, this one is a vertical stretch factor that's greater than the vertical stretch factor for the red graph. So I'm not likely to see an intersection here, since this part is only going to get steeper, and this part will not get steep as fast. So we're done on that side. Suffice it to say, the graph does a nice job of telling me when we have inequality, that is to say, when will the red parabola be above the blue parabola. I can see what that is. Now I can go to my equation or inequality and just do the algebra. So when I do the algebra, I just get a quadratic equation by collecting like terms on one side. I use the zero product rule, sort of. But at this stage right here, I see two factors. And if this was an equation, I would say x equals -3 and x equals -2, which is consistent with my graph. The intersections happen here at two negative values very close to one another. So that's what I showed. But if I took this inequality and just tried to algebraically solve it using the same process that I use for the zero product rule, I would have x plus 3 less than 0 or x plus 2 less than 0. And when I solve both of those, I get x is less than or equal to -3 or x is less than or equal to -2, which is weird to me because it seems like this is redundant. First of all, I'm covering the same stuff twice, but it looks like as long as x is less than or equal to -3, I will always be true. My graph doesn't seem to show that. So with inequalities and quadratics, I can't quite use the zero product rule the same way I used to. I can use it to find the points of intersection. -3 and -2, definitely the places where these are equal. The graph will tell me where they're unequal. So based on the graph, I can see that as long as x is in between -3 and -2, written like this is an inequality or interval notation, as long as x is any number between -3 and -2, the red will be above the blue, and that's going to work for us. That's how you do the work if you have a graph. You basically use the inequality to find the points of intersection. You use the graph to finish and get your total solution set. Now, the way to do this analytically would be, at this point, when I have the quadratic is less than 0, what we would do is make a number line, and on that number line, I would indicate where my zeros are. There's intersection at -2, intersection at -3, and so those are my partitions. Then I'm going to put in values for x that are less than 3 into each of these factors and find out what happens. And in the first case, if I take, for example, -4, this first factor, -4 plus 3, will be a negative number, and -4 plus 2 will be a negative number, and the product of those numbers is positive, which is not less than 0. So we have positive values here. That's no good. Choose a number between -2 and -3, like -2.5. This would be a positive factor. This would be a negative factor. The product would be a negative factor, which is in fact less than 0. So we put a negative there. And for numbers bigger than -2, like 0, for example, this would be 3, this would be 2. That's a positive number, not less than 0. So here we know that only numbers between -2 and 3 work. So this work down here that I'm doing is all in my head, and that's what I would have to do if I didn't have a graph to instantly go from. So you can definitely take the algebraic approach and then use a number line to make sure that your analysis of the inequality is good and you'll get the right solutions. If you were to take a graphical approach, you can get there a lot faster because you have an overview of the whole thing. Let me show you how that works. If we have a graph of 2x minus 1 over x plus 2, and that would be this green rational function right here, and I want all the values for this rational function that are greater than or equal to 1. That's fine. I could use my algebra if I wanted to. That is, let's say I multiply both sides by x plus 2, and then I can collect like terms and get x is greater than 3. Now, when I look at my graph, it seems apparent that when x is greater than 3, the green part of this curve is above the line y equals 1, which means I seem to have found all my solutions. Until I glance to the left and realize that all of this part of the rational function is always uniformly above 1, because it's always above 2, my horizontal asymptote. So all of these x values produce rational function values that are greater than or equal to 1, but it doesn't show up in my algebra because my algebra just says let x be greater than or 3 or equal to 3. So I'm not doing a good job of getting all of my solutions with an algebraic approach, which is enough of a reminder to me that I need to be a little bit more sophisticated. So just using the graph, I can find the rest of my solutions would be any x less than or equal to negative 2. You see what happens is after we cross the vertical asymptote, we go down from negative infinity, up from positive infinity, and now we're all positive, always bigger than 1 in this case. So the algebra tells me one of my intersection points, but my graph gives me a whole new set of points that I wouldn't have seen if I strictly relied on algebra. So in interval notation, here's how I write my solution. Now, of course, we should check our answers. There's other ways to check, but that's not what this video is about. But I would like to show you what you would do if you did not want to use the graphical approach. The first thing is, for inequalities, you need zeros, because if we have less than or greater than 0, we're simply talking about positive or negative numbers irrespective. So in order to make this inequality solvable algebraically, I'm going to need to send the 1 over to the other side by subtraction. And now I want this whole thing to be just one rational expression, not a rational expression minus 1. So I'm going to find a common denominator. Then I'm going to subtract the numerators and end up with a rational greater than or equal to 0. Again, I don't have my graph to work on, so I'm going to use a number line, and here's the kicker. In your number line, you not only need to put your zeros of the rational function, which in this case is x equals 3, you'll also need to include your vertical asymptotes, your undefines. Those are critical values as well. So we put on the negative 2 asymptote and the 3, 0 as our partitions, and we're going to do the same kind of analysis that we did before with... sorry, let me finish the writing here. So with this, I put in a number like 0. I go back over here and say the numerator is negative and the denominator is positive, so we're always negative, and then that's not solving my inequality. But if I go over here like negative 3, the numerator would be negative, the denominator would be negative. That makes a positive ratio, so that's good. That's part of my solution, anything less than negative 2. And similarly, any number bigger than 3, put that in here. You're going to have a positive over a positive, which is a positive number, and therefore acceptable in solutions. So if you're going to solve this using your graphing skills, then it's really easy to do because you just use the algebra to find the point of intersection, and you use the graph to do all the rest. If you're not going to lean on the graph, or if the graph is too complicated for you to achieve, you can simply do the algebra, but you have to look at the approach differently. Instead of just solving like you would an equation, we need to make this whole thing greater than or less than or equal to 0. Then we're going to use our positive negative generators to figure out what the correct solution set's going to be. You can see it's not that bad. It's just more labor intensive than this, and this is a lot of feeling around in the dark, where this is a very clear perception of where all the solutions lie. So you can see where I lean. And if there's not enough evidence that the graphical support is important, I'm going to show you this last piece. If you tried to do this work graphically, you would actually see that the left-hand side and right-hand side, they never actually intersect anywhere. It's kind of complicated to see all this, which is why I went with the black and red, and you can see which one's black and which one's red here. But you can see there is no intersection. What I can see, though, is that from the graph, anytime x is bigger than 2, so here's x equals 2, if we're bigger than that, the red is above the black. If we're between 2 and -1, here we see the black is always above the red, and then if we go from -1 down to -infinity, we'll see the red is always above the black. So I can get the solutions graphically with no problem. Let's take an algebraic approach. The algebraic approach says, let's multiply both sides by the common denominator, which would be, in this case, x plus 1 times x minus 2. So I multiply this side by x plus 1, I multiply this side by x minus 2, and I get this quadratic, which if I actually subtract the x's from both sides, I end up with x squared is greater than -2. Well, that happens to be always true. X squared is always greater than -2 because x squared is always positive and -2 is always a negative. So it appears as though all values of x would make this true. Of course, we don't know that. We know that the correct solution is here because we have the entire graph. But a person who is feeling around without a graph, just feeling around in the dark, they would look at this and say, well, the conclusion must be all values of x make this true. And when you look at the graph again, we can see it's not true. So graphical approach wins the day and definitely beats out the algebra because the algebra gives me no valid conclusions. So instead, I'm going to look at the algebraic approach in its purity, and what the algebraic approach in its purity says is if I have no graph to look at, I'm going to have to take my inequality and use 0 as my basis. So I bring everything over to one side, and then I have to get a common denominator. Once I have a common denominator, I'll subtract the numerators, collect like terms, and then end up with a rational inequality where everything is factored out. Then I'm going to take my critical values, which would be zeros of the numerator and zeros of the denominator, and I would do my little sign game, and that's when I would realize that only values less than -1 or greater than 2 are valid. So at the end of the day, if you want to do anything without graphing, you're going to have to use the number line approach. Strictly speaking, whenever we have a situation where there's a rational inequality or a quadratic inequality, that number line is going to work. But if you want to save yourself the trouble of trying to remember a whole new process, then just learn how to graph well and use your graphing prowess to get those solutions. That's my video. Thanks for watching. Have a good day.